All right, so this video is to quickly cover our alkane reactions. So in your notes, it talks about the chemical reactivity here, and it says that carbon to carbon and carbon to hydrogen bonds are relatively stable. So there aren't a ton of reactions to deal with. There's only these two that we're going to worry about. Combustion, for one, that actually is a review. You've done that before because we had this last semester when we'd have some carbon containing compound. Maybe it was C2H6, which we now know is an ethane, and we'd burn it with oxygen and we'd make products, carbon dioxide and water. The only thing that was hard about that was balancing it, so we should be able to do that pretty quickly. Otherwise, the halogenation is a little bit different. I need to add halogens onto one of my hydrocarbons, and that's where isomers come into play. So that one's going to be a little bit trickier just because you are going to have to look out for isomers there. So if we start out with combustion, again, hardest part about this is balancing it. And also, I guess to start, I could actually have the full hydrocarbon drawn out in a stick model. And if you're going to combine that with oxygen and burn it, I might need a little bit of heat to ignite that. But one of the toughest things is I know that this is a butane, but I need to know how many hydrogens there are. And again, if I use my generic formula, it should be 2n plus 2. So 2 times 4 plus 2 gives me 10 hydrogens. So I need to know what my formula is with how many carbons, how many hydrogens, because I'm going to make those same products that I made a long time ago. And I just need to make sure that it balances. So if I have 10 hydrogens, that means I need 5 waters, which should start warning lights and bells and whistles and whatever you want to call them in your brain, because odd numbers of water never worked before. So I know already that I'm going to need to double this. I need 2 of these butanes, and I'm going to make 10 waters, and that also means I'm going to make 8 carbon dioxides. 2 times 4 is 8. And then I have 16 oxygens on the right, plus 10 more for the waters. That's going to be 26. So divide that by 2. I should have 13 of these diatomic oxygens over here. Remember, the whole reason I doubled the water was to make sure that there was an even number of oxygens on the right side. Because no matter what I multiply by 2 in this situation over here, no matter what I multiply by 2, it's always going to be even, so I have to have an even number of waters. So that could be my butane, right? Otherwise, if it was like a methane combustion, right, which might just be written as CH4 plus O2, because I can't make a stick model for methane anyway, right? I'm going to make a carbon dioxide and water. And again, just balance it appropriately. So as long as I have an even number of waters, which, I need 2 waters, I should be good here, right? But that means I need 2 oxygens plus 2 more. I need 2 of these diatomic oxygens to make 4 total. So that would balance appropriately. I didn't have to double anything here, but that doesn't mean I'm never going to have to double. I always look at this number in front of the oxygen, right? If that's odd, I'm going to have a problem. I'm going to have to double everything. So again, 2 major problems: balancing with your oxygens, and then also, right, if I give you a stick structure, you should be able to actually tell me what the formula is. So you need to be able to do that yourself. But otherwise, combustion's pretty easy, right? Halogenation, also not that tough, really, right? But there are 2 different scenarios for halogenation, and you got to understand that each one is going to be different. So the first thing I can do is I can react with any halogen. So sometimes I'll write X for a halogen because it could represent any halogen, so we might use that right now. It's just a generic formula, right? So if I had this propane and a halogen, right? Again, that halogen, if I just have one of these, right, I actually have two of these X's combined. Again, it would probably be a chlorine combined to another chlorine, or a fluorine and another fluorine, but X is just a generic for any halogen, right? And I'm going to take one of these X's and I'm going to put it on a carbon. And that's where the situation where if this is different than this, I have to count them both, right? Because those are both isomers, right? Now, if that was a methyl that I was attaching to carbons, then I could only have that first option. I could only have a 2-methyl propane. But since this is an halogen that I'm adding onto this carbon chain, right, it doesn't make my chain longer to put it on the one carbon. So I actually have these two different options. I could have the first one or the second one. But I also need to understand that in order to do that, I had to replace a hydrogen either on this carbon or on this carbon, right? I mean, there were 2 hydrogens here, and there were technically 3 hydrogens here to replace. But I'm replacing one of the hydrogens on that carbon chain. So that hydrogen combines with my other atom, my other halogen atom. So if I'm putting this X on the carbon chain, I'm going to take the other X and I'm going to combine it with that hydrogen that I replaced to make a hydrohalogen, right? So again, this is just a generic form right now, right? A real example would look more like this, where I could have, let's say this butane plus chlorine, right? Diatomic chlorine. And I'm going to end up with a halogenated hydrocarbon over here. So I'm going to put a chlorine on one of these carbons. And then I'm going to have a hydrohalogen, a hydrogen chloride as a byproduct, right? But I may or may not have isomers for this first thing. And in this case, I actually do, because again, although if I put that chlorine on the third carbon, it'd be the same as this first example that I made. Technically, I can add in the 1 and the 4 as an option. So this is different than that. So there are 2 different isomers right now, right? So knowing that there could be different outcomes, different isomers, is important for halogenation. But otherwise, there's another version of this, right? We're assuming that there's only one chlorine here to react. If I give you an example in the future, so I got to insert a page real quick. If I give you an example that looks like this in the future with, chlorine and a blank in front of it, meaning I could have any number of chlorines, right? I actually want you to replace every hydrogen on that halogen because it would happen, or every hydrogen on that hydrocarbon, because it would happen one after the next, right? If you had an excess of chlorine, you could actually replace all of the hydrogens and have 3 chlorines on this carbon, 2 chlorines on this carbon, 3 chlorines on this other carbon, because there were, as you can see, there were 8 different hydrogens to replace, but that also means I'm going to make 8 hydrogen chlorides, and I also needed 8 of these diatomic chlorine molecules to make this work, right? The only other thing I'm forgetting right now that I technically need to have in there, next chapter is going to be really important, is there also needs to be a catalyst, right? For halogenation to occur, I actually need to have light, UV light specifically, but I need light to make this reaction work, right? So it wouldn't actually happen in the dark, right? When there's no sunlight available or no light source that creates a significant amount of UV light. But again, if I just put light above the arrow, you're going to assume that there's at least UV light in there, right? I'm not being specific, but technically it's the same. So as long as I have light available, this reaction should work. But again, if I want you to replace one hydrogen, I'll put a 1 in front of the halogen, right? On your quiz, on your test. If I want you to replace all of the hydrogens, I'll put a blank there, and then you just do what you got to do. So again, shouldn't be terribly difficult. Just want you to be able to get through those reactions. Some of the connections to this, obviously I'm supposed to make carbon dioxide and water as my products of combustion, but you guys know that sometimes that doesn't work out quite the way you want to. So if you have incomplete combustion, it can make carbon monoxide. We talked about that before, how it blocks your oxygen transport to your cells because that carbon monoxide attaches to that iron, that ferrous iron in your blood, right? Really, really attracted to that carbon monoxide. It looks like this kind of. And it's so attracted to the carbon monoxide that it doesn't attract oxygen like it normally would, right? It just carries that carbon monoxide around, and then your cells don't get the oxygen that they need. So carbon monoxide poisoning is really dangerous. Right? You got to have one of those detectors in your house, in the basement if you have a natural gas furnace or even a propane furnace because you live in the country. Otherwise, you guys are also aware that there's something left behind a lot of times when you burn something, right? That ash, that soot that's left behind, right? Those are also part of that incomplete combustion. So the fact that when you burn a log in your fireplace, there's ash left over, you know that that combustion is going to be incomplete, right? The only way you can get complete combustion is by having a lot of oxygen available. So anytime you're burning something, you're probably going to make some carbon monoxide, and so you got to be careful, right? You have to have proper ventilation with a fireplace too, right? Otherwise, CFCs, you've probably heard of those and how they kind of affected our ozone layer for a while. That has actually, for the most part, repaired itself since we stopped using them, right? We're not putting any more CFCs into our atmosphere, so the ozone layer has pretty much replenished itself at this point. It's back to normal-ish levels in most places. There are probably still some problem areas, and we have to keep avoiding situations like this. But essentially, CFCs are those halogenated hydrocarbons that we were talking about, right? The original CFC, right, Freon, had like fluorine, chlorine. So it's actually like that one fluorine, three chlorines, right, on this central carbon, right? So this is a methane that's halogenated, right? It's got three chlorines and a fluorine on it, and this is what we called Freon, right? It was used as a refrigerant, right? There are other versions of Freon. You could actually have an ethane that's been halogenated. So maybe there's a chlorine here, a couple fluorines, and maybe these are all fluorines over here, right? This is a specific one that I saw online a little bit ago because I wanted to look up some different examples for you guys. I knew a few, but not a ton. So this is another version of Freon, right? Freon up here is specifically Freon 11, whereas this one down here is Freon 115. What either one was used for is as good your guess as mine, but they are refrigerants, right? So were they used in your air conditioner in your pickup, or were they used in an actual refrigerator? Who knows, right? But some of these things were also used as propellants, so like hairspray and things like that in the 80s, 70s, right? That's when we were having issues with this, right? That's when we started realizing that we were depleting that ozone layer, and we probably shouldn't do that anymore. These molecules react with UV light, just like we were talking about before. UV light created these molecules to begin with, but they can react with UV light to make these free radicals, which would essentially be a chlorine that's looks like this in terms of our Lewis dot structures. And this is a super reactive version of chlorine. It's not very stable. It's ready to steal an electron from something else, and that's why it reacts with the ozone layer, right? And it creates this chain reaction where one molecule reacts with another, and it depletes that ozone really rapidly, right? Otherwise, like I said, there could be other versions of this, right? I was going to draw another one, but not really that big of a deal. So as long as you have some halogens attached to a carbon chain, right, those could be CFCs. Otherwise, that's it for the chapter, really. The only thing left to talk about is how there are a lot of different functional groups that are going to be coming up in the near future. So this slide would basically just be a heads up for what you're going to have to deal with down the road. So we have a lot of different things that are going to come down the road. We have single bonds between carbons right now. Next chapter, we're going to add in double bonds, triple bonds. We're even going to add in this new thing called an aromatic ring, where you have double bonds that are moving in a circle. We're going to have alcohols. We're going to have aldehydes. We're going to have ethers. We're going to have thiols. We're going to have amines. We already talked about hydrohalogens, halogenated hydrocarbons. That's what I meant to say. We're going to have, what else am I missing? I'm missing a ketone. I'm missing a carboxylic acid. I'm missing, this is what we call an ester, not to be confused with your art teacher, but this is called an amide. So there's just lots and lots of stuff coming that it's going to get kind of crazy kind of fast, but you guys can handle it.